So we're talking about what happened last laboratory about the DenseNet architecture. So in the laboratory, the previous lab, the DenseNet or densely connected convolutional networks, um, we're building it from scratch and comparing it with a pre-trained DenseNet um, one-to-one. So the entire laboratory revolves around one question. Instead of passing information layer by layer and occasionally skipping layers like ResNet, what if every layer could directly access the outputs of all previous layers? So the problem DenseNet tries to solve, in a traditional convolutional neural network, we have the input after the input convolution 1, convolutional 2, convolutional 3, and convolutional 4. So each layer only sees the output of the previous layer. As the networks become deeper, early features may get diluted, information can be lost. Layers may relearn features already discovered earlier. So, ResNet solution is introduce the skip connections. So, we have we preserve the inputs. So whenever the output of fx get something approximate to 0, then this preserved input and will be the way to the path to continue to flow. So the original input can bypass several layers. This helps the gradient flow. And DenseNet solution goes much further. Every layer receives all previous features maps. Example, from the layer 1 output, so the layer 2 input is the layer 1, layer 3 input is layer 1 and layer 2, and layer 4 input is layer 1, layer 2, and layer 3. So the bracket means of the Turkey-cat is concatenation and not addition. So the core idea is to feature reuse. DenseNet assumes earlier layers already learned useful patterns. Don't throw them away. Layer 1 learns edges, layer 2 learns corners, layer 3 learns textures. Instead of replacing all the information, textures only, and DenseNet keeps everything. Edges plus corners plus textures. So all layers can reuse previous knowledge. So dense layer. So in the laboratory first builds the dense layer class and in that module. This is the smallest building block and structure. A dense layer contains the bottleneck and then a ReLU and 1 by 1 convolutional for the bottleneck, and ReLU, and 3 by 3 convolutional, and concatenate with input. So bottleneck layer inside the dense layer, 1 by 1 convolution. This is called bottleneck. The purpose is to reduce computation. Example, if you have the input of 100 channels and without the bottleneck, the 3 by 3 convolutional on the 100 channels, that is expensive, and instead from 100 we reduce it to 48, and then we convolution it by 3 by 3. That's much more cheaper. So what is BN size, or batch number, bottleneck size? So the bottleneck size we use is 4 and the growth rate is 12. Therefore, so we multiply it, then it becomes 48. So the bottleneck outputs is 48 channels. So what is growth rate? This is one of the most important DenseNet hyperparameter. So the growth rate we set it at 12, and each dense layer adds 12 new feature maps, not 12 total channels, or so 12 new channels. Example, input is 3 channels, dense layer adds 12 channels, the output is 3 plus 12 is 15 channels, because DenseNet concatenates. Next is why channels keep growing. In the normal CNN or convolutional network, this is sequential, like 64 after the 64 and other than 64. So the DenseNet after the 64, 76, 88, 100, and 112 channels. So because every layer contributes new feature maps, this growth is called knowledge accumulation. Next is dense block. The next class is dense block. Dense block simply stacks many dense layers. Example in the dense block parameter is the input channels, growth rate, and number of layers. So the layer 1, like for example, we inputted 3 channels and adds 12 channels, so the output is 15. Layer 2 is 15 channels and adds 12 channels, and then 27 channels. So channel growth becomes from 3, 15, and 7. This is exactly what we did in the laboratory. We use and we verify it using the torque info summary. Next is dense connectivity. Imagine 4 layers, traditional convolutional neural network, 1 and 2 and 3 and 4. But the DenseNet, every layer receives or earlier outputs. This creates the dense connections. Next is transition layer. A problem appears. Channels keep growing. Example, from 64 channels to 56 to 512 and 1024. That the memory may explodes, and DenseNet solve this using the transition layer. So the purpose of it is compression. It uses the 1 by 1 convolution to reduce channels. Example is 256 channels and 128 to 128 channels. Next, its purpose is downsampling. We do the average fooling 2D to reduce the spatial dimension. So from 128 by 32 by 32, it reduces from 128 by 16 by 16. Think of transition layer as compress knowledge and prepare for the next dense block. Next is DenseNet architecture. The full network is from the input is 10 to dense block 1, transition again, dense block 2, transition, dense block again, and then transition, and dense block 4, and global average pooling, and then classify dense classifier. So the lab stem is convolution 7 by 7, and this ride of 2 followed by the pooling. So let's say we input the 3 64 by 64 and becomes roughly 64 by 16 by 16. The stem aggressively reduces image size before entering dense blocks. So dense block pattern is the lab summary shows from 64 channels to dense block to 156 channels. Why? Because many testers keep adding new features. The channel count accumulates. Next is training the custom DenseNet. In the laboratory, trains DenseNet from scratch on. We use the 21 classes. Example, the harbor, airport, forest, mobile home park, residential areas, for only 100 images per class, which is very small. So in the training setup, we use the cross entropy loss and the optimizer Adam with the learning rate of 0.001, and we set the epochs of 20. Why DenseNet works well? DenseNet is extremely data efficient because earlier features we reuse it and we are not going to relearn it, which is expensive. So the benefits: better gradient flow, every layer has distinct paths to loss. Feature reuse, no need to rediscover edges repeatedly. And fewer parameters compared with similar deep architectures. And strong performance, especially on a small data set. So, results of custom DenseNet. The lab expects around 75% plus validation accuracy. And after training from scratch for a 21 class datasets with limited data, we achieve from the range of 75 to 80%, and that scale is very strong. And we did the confusion matrix analysis. Classes with unique structures perform best. Examples: the baseball diamond, the harbor, mobile home park. Why? Because their visual patterns are distinctive. So classes that may be confused, dense residential versus medium residential, or different infrastructure categories, because aerial views look similar, such kind of things. So feature extraction, this is transfer learning. The second half of the laboratory introduces the DenseNet 1-to-1. It's a pre-trained on ImageNet. And as entity PyTorch, of course, instead of training everything, we freeze the backbone, we turn off the gradients, and we train only the final classifier. And why this works, ImageNet already taught DenseNet edges, textures, shapes, patterns, objects from millions of images. We reuse this knowledge. So the result is custom DenseNet is of 20 epochs is around 75 to 80%, and feature extraction is 5 epochs, often higher accuracy. It's much less training. So the key concept here in the DenseNet is feature maps is the channels. When in the DenseNet it says add subchannels, it means we add 12 feature maps, and the feature maps is the learned pattern that we're going to show. And the growth rate means each DenseNet creates new feature maps. And concatenation, we get every details of learned features and not adding them or mixing them to get a result, but rather to use those learned features. So dense layer produces new features and concatenates them with old features. And dense block stacks dense layers and accumulates knowledge. The transition layer reduces channel count, spatial size. So in DenseNet, in ResNet says reuse information through addition, that's a ResNet. But in DenseNet, we preserve and reuse all previous feature maps through concatenation.